So let's consider phase transitions. In particular, let's consider evaporation versus condensation and also make it clear that we understand the difference between vaporization and vapor pressure. So first of all, vaporization and condensation are opposite processes. Vaporization is endothermic, heat is going to be put in. Condensation is exothermic, heat is going to be released. So vaporization, here we know that corresponds to a liquid going into a gas. So condensation is the reverse, and that is a gas going into a liquid. The values of their heat are simply opposite in sign. In an open container, vapor molecules spread out faster than they can condense, and the rate of vaporization is greater than the rate of condensation, so we're not going to have a dynamic equilibrium, and we're going to lose liquid. This is different than here if we have it in a closed container. In a closed container, the rates of evaporation and condensation are going to be the same, and we are going to get a equilibrium, and we're going to get a nice vapor pressure up here. But if we take that lid off, we are going to look at a net process of gas loss, and that is going to be vaporization. So let's consider the processes. We can go from a solid to a liquid. If we go from a solid to a liquid, we call that melting. Of course, we can't make it that simple. We're going to call that fusion. Fusion means melting. If we go from instead a liquid to a solid, that is going to be freezing, and it's simply the opposite process with the opposite sign. If we go from a liquid to a gas, that's vaporization. If we go from a gas to a liquid, it's condensation. And we can go all the way from a solid to a gas, and if we go from a solid to a gas, that is sublimation. The reverse process can also occur, and that is called deposition. So in order to do this, we need to know what we're doing in terms of our process. So note, we need to consider boiling, and we can consider freezing. Let's just look at water briefly. We know that water boils at 100 degrees Celsius. And when boiling, it is going to go from, remember the nice little bubbles of gas at the bottom of the liquid, coming up to the top of the liquid and escaping. That is not vaporizing. Vaporizing is a process where our gas is escaping just due to kinetic energy of the molecules at the surface. Boiling is the process of formation of these gas molecules inside of the liquid. So boiling occurs at a set temperature. So if we are going to boil a liquid, it is going to occur at its boiling point. Freezing is the same way. Freezing occurs at its freezing point. So if we can consider water, for example, water we know boils at 100 and it freezes at 0. Now these are the normal boiling and freezing points, meaning where the external pressure here is 1 atm. If we have a temperature less than 100, the water is not boiling, it is heating. If we have a temperature of, let's say, less than 0, our ice is not melting. It is, in fact, going to be changing the temperature of our ice. So with that thought in mind, let's look at the mass of water that can be vaporized with this amount of heat at 100 degrees Celsius. So we have two equations. We are either at a phase change, and if we are at a phase change, we are going to be at constant temperature. If we are at a phase change and we are at constant temperature, our heat Q is usually given in moles multiplied by the delta H of the process. So let's just take and figure out how much heat is going to be required, or how much, water is going to be vaporized with this amount of heat at 100 degrees Celsius. So we need this value. Well, we can look this up, but we can be given that the delta H of vaporization for water at this temperature is 40.79 kilojoules per mole, and we can plug this in. 155 kilojoules is going to equal moles multiplied by the 40.79 kilojoules per mole, and we can solve for moles. When we solve for moles here, we're going to discover that moles is equal to our 155 divided by 40.7, and when we do 155, we divide it by 40.7, we're going to get that our moles are equal to 3.80. And if we want grams from that, because we're asked for our mass, we're going to multiply that by 18 grams per mole. We're going to realize that we can vaporize 68.4 grams of water using 155 kilojoules of heat at this temperature. So this will be our mass. So we can take understanding what a phase change is constant temperature, and we can figure out the amount of heat. So let's look at a similar process for ethanol. Now we're looking at the amount of heat that is released when the stuff condenses at its boiling point. So we're taking ethanol, C2H5O8, and we are going from a gas into a liquid. We go from a gas into a liquid, heat is released. This is going to be exothermic, and we're going to have a negative value. To do this, we have to realize that delta H of condensation for our ethanol is going to equal minus delta H of vaporization. It is the reverse process and is going to have the opposite sign. So our delta H of condensation is a minus 30.8 kilojoules. We want our heat Q. We know that our heat Q will equal our moles multiplied by the delta H. So the heat Q is going to equal 90 grams. We're going to divide by the molar mass of ethanol, so we have 1 mole for every 46 grams. We're going to use our enthalpy. It's going to be a negative 38,000 or 38.6 kilojoules per mole. And so if we put our values together here, we're going to get that our heat that is released, again, the negative sign here, is going to equal minus 75.5 kilojoules. Simply taking the grams and going into moles and multiplying the heat that is going to be released at this phase change. But what if we go through more than one phase change? So let's imagine that what we have here on our x-axis is the amount of heat added, and this is the temperature. And we are going to start out at ice, which is what we have down here, nice and cold, and we're going to keep adding heat, and we're going to keep adding heat. And as we do, we realize that if we are at less than 0 degrees Celsius, we are going to have to heat our ice. And we know we have to heat our ice because ice doesn't melt less than 0. Ice melts at 0. So we're going to have to do right here, and we're going to have to heat the ice. Now, when we're done heating the ice and our ice is at 0, we can melt our ice. So our solid is going to begin to melt at 0. Once we have all of our ice melted at 0, we are going to have water. So between 0 and 100, we are going to have to heat our water. We're going to have to heat our water because water doesn't boil at 100 or at 0. Water boils at 100. And we're going to have to add enough heat to get to that temperature. Once we have all of our water as a liquid at 100 degrees Celsius, we can begin the next phase change. We're going to begin the next phase change by adding heat to this. Temperature is going to remain constant as all of the water as a liquid is converted to the gas. And when all the liquid has evaporated and converted to gas, we can finally heat up our gas. Realizing again that at phase changes, our temperature is constant. As we go in between phase changes, we are going to have to add heat until we get our solid or a liquid to the correct temperature it needs to be in order to undergo a phase change. So let's consider some phase changes. We're going to take a water bottle out of the freezer with 250 grams of ice in it at an initial temperature of minus 10 degrees Celsius. And we're just going to ask how much heat do we need to add to it before we can drink all of it at a temperature of 5 degrees Celsius. So what are we going to do? Well, we know if we have ice, we know that ice melts at 0. So at minus 10 degrees Celsius here, ice is not going to melt. So we're going to have to do 3 separate processes. One, we're going to have to heat the ice. And we're going to have to heat the ice from minus 10 into 0 degrees Celsius. Once we have all of the ice heated to 0, we can go to step 2. and we can melt the ice. When we melt or we have fusion, we're going to do this at constant temperature. And once we have melted all of the ice and we have all water as a liquid, we are going to heat our water. This is 3 separate processes and 3 separate equations. So one, at phase changes, our heat Q will equal moles multiplied by a delta H. But if we're going to heat it and we're going to have a change of temperature, so here in step 1, we're going to go from -10 to 0, and in step 3, we're going to go from 0 to +5, and we're going to have a change in temperature, we have a new equation. And our new equation is Q is equal to mass multiplied by the specific heat capacity multiplied by delta T. Specific heat capacities will be given, or you can look them up. And delta T, delta being change, is always going to be T final minus T initial, because if you do it in that direction, you're always going to keep track of the sign. So with that in mind, step 1, 250 grams of ice heated from -10 to 0, and we're going to need the specific heat capacity, and the specific heat capacity for ice was given on the previous slide, and it is 2.03 joules per gram degree Celsius. So our heat Q is going to equal 250 grams multiplied by our specific heat capacity, joules per gram degree Celsius, multiplied by our delta T. Well, our final temperature is 0. Our initial temperature is -10. That's going to give us a positive value for our delta T, which is good because we're adding heat. And we're going to find that our Q for our heating the ice is going to equal 5075 joules. That's step 1. Step 2, we're going to melt the ice. Well, to melt the ice, we're going to have to add the amount of heat required to melt, which is our delta H of fusion. That's also given. Our equation here is Q is equal to moles times delta H. And if we plug that in, our Q is going to equal our moles, 250 grams. 1 mole for every 18 grams, this is water, multiplied by our delta H, which is given as a value of 6.01 kilojoules per mole. Because our previous value was in joules, I'm going to put this in joules, and I'm going to have 1,000 joules per kilojoule, so I can add this when I'm done. And when I'm finished this, I'm going to get 83,470 joules. So for part 2, it's going to be significantly more heat. Why? Because we're doing a phase change and we're breaking a lot of intermolecular forces. Step 3. Step 3 is we're going to heat the water. Well, if we heat the water, our equation is going to be Q is equal to mass specific heat capacity delta T. We have a different specific heat because this is no longer ice, this is water. So we're going to have our heat Q is equal to 250 grams multiplied by 4.184 joules per gram degree Celsius. Again, that will be given, or you'll look it up. Multiplied by delta T. Well, our T final was 0. Our T initial at our phase change where our ice has melted is 0. And we're going to get a Q for this of 5230 joules. Now, to get the total for this, we're simply going to add these up. And we're going to take our Q for heating the ice, add it to the Q for melting the ice, with Q for heating the water, and we're going to get our heat total will equal 93,780 joules.